Today I will explain about the operation of this tunnel diode. So this tunnel diode was given by Esaki. Okay, so the theory of this tunnel diode was studied by Leo Esaki in 1958 because of tunneling effect he proposed or he studied. He got a Nobel Prize. That is, tunnel diode is nothing but a PN junction diode that is of heavily doped p-type and n-type material. Due to heavily doped, that is the concentration of in normal PN junction diode, one impurity atom will be added for 10 power 8 intrinsic semiconductor material atoms. But here we are going to add one atom for 10 power 3. So there is much increasing in the doping process. That is, more number of impurities are we are adding here. So because of that, what happened? The depletion region will be decreases. It will be very narrow, and it is of nanometers. Okay, nanometers means that it is 10 power minus 9 meters. Okay, so that is what how the tunnel diode will be formed by using heavily doped p and n type materials. And the symbol here also we have anode and cathode. Okay, in 1973. So this is about the introduction. Tunneling is nothing but the penetration of the electrons from n side to p side through a narrow depletion region is called as what? A tunnel diode, tunneling process. Okay, so because of this tunneling process, there is a current flow is taking place. Because of that, this diode is called as what? Tunnel diode. Okay, you can observe here, this is nothing but the valency band, and this is nothing but the conduction band of n-type, and this is nothing but the valency band of p-type. So they will overlap, and the electrons that are from n-type is penetrate into the valency band of p-type because of small depletion width. So this process is called as what? Tunneling, and because of this process, these diodes are called as tunnel diodes. Okay, so this is what about the introduction, and we'll go with the band diagram of tunnel diode. That means in the final exam also they will ask you that explain the operation of tunnel diode by using the concept of band diagram, or by using its band diagram. Okay, then how we can say that here in the p-type valence cell and n-type conduction band are overlapped? How we can say? We will see by taking the basic equation what we have. Okay, about the Fermi levels. Okay, so and remember that they don't ask directly explain the operation of tunnel diode, but they will ask you that explain the tunnel diode operation with band diagrams. Okay, so that's what we are going to see, the working of the tunnel diode, right? So here this is nothing but what we have is this is normal PN junction diode band diagram, and this is nothing but the tunnel diode band diagram. So you all know that what is band diagram means. It consists of valency, and it represents with valency energy level, and at the same time conduction band energy level. In between that we have Fermi level. So here I am taking that EC is nothing but the conduction band of P side, and EV is nothing but the valency band of P side. And in between the conduction band and valency band, we have forbidden energy gap. That gap I am representing here as EZ. Okay, so we all know that in P side semiconductors, the Fermi level will be present in the valency band. For a normal P-type material, not highly doped, for normal P-type material, we have seen already that what we call in the Fermi level position in intrinsic and extrinsic semiconductor. In the first unit, we have studied that. So the Fermi level in P side is nearer to the valence cell energy level, and at the same time in the conduction band, it is nearer to the conduction band. It is nearer to the conduction band energy level. Okay, so these things we have to see here. What is Fermi level of conduction band and what is n-type semiconductor and p-type semiconductor in a tunnel diode. We have to see that. Okay, so for that condition, I am taking that here EF is equal to EC minus KT by KT log NC by ND. You all know that this NC is nothing but energy states, and ND is nothing but the donor atoms what we have to add to form an n-type material. So here we are going to see that if for a normal PN junction diode where the Fermi level is present, or if you consider a heavily doped material, so where the Fermi level will consist, we have to see by taking this equation into consideration. So EF is equal to EC minus KT log NC by ND. NC is nothing but energy density states, and ND is nothing but carrier concentration, that is impurity concentration, sorry. Okay, impurity concentration, that to donor atoms. So here for normal n-type material, we will consider generally ND is less than NC. Okay, so ND is less than NC means log of ND by NC. So its value is negative value. So here we have log of NC by ND is nothing but if ND is less than NC. So what happened here, ND is less than NC means it is more positive. More positive means EF is equal to EC minus, actually EC is present here. This diagram is somewhat wrong. Here EC is presented, the lower energy level of conduction band of n-type, but Fermi level for normal diode is nothing but if donor atoms is less than the concentration NC. So what happened here, this value will be more positive. Log of more positive is more positive value here. So EF is equal to EC minus. EC energy level is here, but EF we have to place here, right? So that is nothing but the Fermi level is nearer to the minimum energy level of the conduction band in normal PN junction diode. So if you consider that if ND is very greater than NC, if ND is very greater than NC, so what happened here? If ND is very greater than NC, so what happened? NC by ND. Okay, so ND is here, the numerator is very greater, denominator is very greater. So it consists of log of small value. So that is nothing but log of small value to the base C is nothing but also very small value. So EF is equal to not very small value, it is negative value we will get, because if NC is very less than ND, so here log of NC by ND is nothing but we will get the negative value. Previously we will get because NC is greater than ND, we will get log of more positive value is there, that becomes positive here, but here it is 1 by some value will get, that means what, ND is greater than, ND is denominator is greater than numerator, so log of that value is nothing but you will get the negative. So negative of negative, that is positive. So EF is equal to EC plus some value. So where the Fermi level will be present in the n-side extrinsic semiconductor, that is n-type semiconductor or n-type material, is nothing but it is above the minimum energy level, because here if you consider this condition ND by ND is greater than NC, the denominator is more positive. So log of this value is nothing but you will get negative minus plus you will get. So EF is equal to EC plus some positive value. So EF is equal to EC. EC is the minimum energy level of conduction band plus some value is nothing but EF. So I am representing EF above the conduction band, but here it has to be nearer to here. We have to draw that one is wrong actually, the diagram. So I will show you that. So actually here it has to be, that is EF. Okay, but it was gone wrong. That is here we have to represent EF for normal n-type material. But if you do the heavily doping means, that is donor concentration is more, so it will be above this like this. It is correct, but it is wrong. This one is not here. Okay, so this one is correct for normal p-n junction diode, but it is highly heavily doped means it will shift upwards. That is what this equation states. And another thing is we have EF is equal to EC, not EC here because it is valency band. The Fermi level is present in valency band. So EF is equal to what is the formula? EV plus KT log of NV, that is NC means here NV you will get conduction band and valency band. Valency band energy states NV by NA. NA, why it is called NV by NA? This equation we can write it as, I will write here. This equation we can write it as EC EV plus, for p-type material I am writing KT log of NV by Na. So it is p-type material means that consists of acceptor atoms. N-type material, for that we are writing here Nd. So here EV plus KT log of Nd NV by Na. So here also the acceptor concentration is very more because it is p and n-type material in our tunnel diode is concentration is very high. So because of that, here also what happened here, the denominator is more positive. Denominator is more positive and numerator is lesser value. So this value we will get is negative value. So the equation becomes EV minus some positive multiply with negative value. So you will get is negative EV minus some value you will get. So EF is equal to here, where it might be is nothing but valency cell energy level minus some value. So here, if suppose in the p-type material EV is the highest energy level of the valence band, then EF is nothing but below that. Below that means why it is below? That is EV minus some value. So because of this, we can say that if you observe this one and this one, the Fermi level, that is the probability of finding an electron, is 1/2. Here EF is present below this one, and that is below this valency band of p-type material, and at the same time the EF is present above the conduction level of the n-type material. So there is a coincidence of overlapping of valency band of p side and conduction band of n side, if you consider the tunnel diode, and the depletion region is very less. So this is the concept. I have mentioned that in this tunnel diode there will be a overlapping of valency band of p side and the conduction band of n side. So what is the reason means? That's what I have explained by taking into consideration Nd is greater than Nc and Nd is less than Nc. Okay, if you understood this concept, next it is very easy to understand the operation of this tunnel diode. Okay, so I will erase 1 minute. So this is what how the difference between the band diagram of normal p-n junction diode and at the same time band diagram of tunnel diode, because it is heavily doped. So how the Fermi level will shift up and down in conduction band as we increases the doping concentration. So in n-type material, the Fermi level is present above the minimum energy level of the conduction band, but the Fermi level is present below the valency band in the p-type material. Okay, the reason also I have explained here. So if you know this knowledge, so we can go with our actual operation of tunnel diode. Okay, so you can observe here. Step 1 is what I am taking, unbiased tunnel diode. When no voltage is applied to the tunnel diode, it is said to be an unbiased tunnel diode. In tunnel diode, the conduction band of the n-type material overlaps with the valency band. So I already told that conduction band of n-type material is overlap with the valency band of p-type material. So therefore there is just some movement that can be takes place because the depletion width is very less. Okay. So here in tunnel diode, the n-type material conduction band overlaps with the p-type material. Because of this overlapping, the conduction band electrons at n side and valency band holes at the p side are nearly at the same energy level. So when the temperature increases, some electron tunnel from conduction band n region to the valency band. So if there is no increasing in the temperature, there is no tunneling will takes place. Only as it is, the holes and the electrons will be present in the conduction band and valency band respectively. Okay, so whenever a temperature increases, what happens? Some of the electrons that are present in the conduction band is travel into the valency band. Okay, valency band of the p region, and similarly holes will tunnel from valency band to the from the valency band of p region to the conduction band of n region. Okay, however, the net current flows will be zero because an equal number of charge carriers. So one electron is travel from this point, so the hole will travel from this point to this point. So equal number of charge carriers are traveling in the opposite direction. So therefore, the current will be zero because at this point there is a possibility of recombining of these holes and electrons. So because of that, there is no current we can consider here. That therefore, in the unbiased tunnel diode condition, what happened is there is no tunnel current. Tunnel current means whenever the electrons moves from n-type to p-type and p-type to n-type, that is not moving, it is penetrating. Okay, then there is a current will flow, but here there is no penetration of those electrons and holes will be takes place. So because of that, the current will consider is zero. So this is what unbiased tunnel diode. Okay, so next we'll go to the step 2. Small voltage is applied to the tunnel diode. So I am applying now a small voltage, external voltage. So what happened here, if I apply the external voltage, what happened is uh, the Fermi level slightly shift upwards. Here you can observe the Fermi level slightly shift upwards. So because of that, there is a more possibility of shifting of the electrons from n side to p side. That means initially it will be like this. Initially it will be like this. So there is no bias means, sorry, initially it is like this. It is, this one is valency band and this one is conduction band. So what happened if I apply, a voltage, what happened is slightly the conduction band will be rises. The conduction band will be rises and almost the valency band and conduction band will be coincide like this. So electrons freely moves from this point to this point directly. That is the what the point. If you apply small voltage applied, so there is not completely coincide like this, not completely coincide like this, but like this it will be there. This is conduction band and this one is the valency band. So whatever the space that is there here, through that space the electrons will travel from n side to p side. That's what here it is clearly represented. You can observe here clearly represented, the electrons will move from some part is coincide, not all the part of valency band. You can observe up to this point only the conduction band is overlapped with the valency band of p-type region. So some space is there. Through that space the electrons will travel from this point to this point. So there will be some current, there will be some current will flows. So when a small voltage is applied to the tunnel diode, which is less than the built-in voltage of the depletion layer, no forward current flows through the junction. But however, a small number of electrons in the conduction band of the n region will tunnel to the empty states of the valency band in the p region. This will create a small forward bias tunnel current. I already told that as we increases, the barrier height will be decreases. As we increases the what we call, as we increases the forward bias voltage, what happen? Depletion region width will be decreases again. So this is the depletion region height. So the conduction band will move upwards so that the valency band and conduction band will be overlapped for p-type and n-type conduction band. So because of that, there is a small amount of number of electrons will flows from n side to p side. So the current will rises here. A small current will flows. This is second case. And we have third case, applied voltage is slightly increased further. So what happened if I applied, when the applied voltage is slightly increases, what happened is, so then there will be a coincide of both. This one is the N conduction band and this one is P valency band. So like this, there will be a direct overlapping. That means they will the p side valency band and n side conduction band will be like this. So what happened here, if it is like this, the electrons from n side to p side will penetrate easily and the depletion region will be decreases. So you can observe here the depletion region is vanished, and that is the conduction band and the valency band of p side is this one, the valency band, and the conduction bands of n side is this one. So both are overlapped. There is a direct path established between the n-type conduction band and p-type valency band for the electrons. So like this, the penetration of electrons will take from n side to p side, and the voltage applied to the tunnel diode is slightly increased. A large number of free electrons at a n side and holes at p side are generated. Because of this increase in voltage, the overlapping of the conduction band and valency band increased. That means there is a direct path will be established as we increases the voltage value. Okay, so that is what here the coincidence of coincide of this energy level, valence energy level and conduction band. So because of that, the current rises greatly. Okay, because more number of electrons penetrates through the n type to the p type, because the whatever the minimum barrier is there, that will be vanished as we increases the applied voltage. Therefore, direct penetration of electrons will take place from n side to p side. So there is a movement of electrons. So directly the current will be rises. For a small voltage applied to the tunnel diode, there is small current increases. But if you observe here, it is the maximum current here. The maximum tunnel current will flows because both will be coincide. Both will be coincide. So that's why here maximum current will be flows. So if you further increases, what happened here? So if you further increases whatever the thing that is the present, the coincidence of p type and n type. So if you further increases the positive voltage, forward bias voltage, what happened? Again the conduction band will rises. Again the conduction band will rises. Therefore the current will be decreases, because previously it is like this. For a at particular point, peak voltage at a particular point, the current will be maximum at that voltage is called as the peak point or peak voltage. After crossing the peak voltage, what happened is suddenly the valency band will be present like this, but the conduction band will go upwards, and again the coincidence will be not in exactly coincidence. So it will reach above, the conduction band reaches above like this, what I have shown in the diagram. So previously what happened, these two are in the same level, so maximum electrons will travel from n side to p side, but here it is not the case. So this conduction band rises up. Because of that, there is a small path is there between n type and p type materials. So because of that, small number of electrons will flow, so the current will be decreases like this. So it reaches the maximum voltage, maximum current, when both the valency band and valency band of p side and conduction band of n side exactly in a same position. Okay, so but after that, what happened, if you apply further increasing in the voltage, what happened is here the current will be decreases. Okay, so that is current, we can start that one as tunnel current starts decreasing. Okay, and next final stage is, if you further increases, what happened is if you further increases, what happened, there is a direct conduction band of p type and conduction band of n type will be overlapped. Conduction band of p type and conduction band of n type will be overlapped. So only the electrons will flows from n type to p side, p conduction band, not valency band. Therefore it acts like a normal p-n junction diode. So as we increases in the normal p-n junction diode, so the current will be maximum. After reaching this lower value, up to this point, lower current will flows. After that, if increases further, what happened, it becomes normal p-n junction diode operation, because the conduction band of p type and n type will be, there is a movement of n type conduction band to p type conduction band. So there is no there is more amount of current will flows. After reaching the zero tunnel current, maximum forward current will flows, because it after, if you increases very largely the input voltage, what happened is, so the conduction band of p type and conduction band of n type will be overlapped. So there is a movement of electrons that taken place from n type to p type. Okay, there is no tunnel current here. The maximum forward current will flows. If the applied voltage is largely increased, the tunneling current drops to zero. At this point, the conduction band and valence band no longer overlap. Okay, and the tunnel diode operates in the same manner as normal p-n junction diode. Okay, so this is what how we have the characteristics of this tunnel diode. Okay, so this is how you have to explain in the final exam if they ask the question that explain the concept of tunnel diode operation by using band diagram. So I have shown here the characteristic curve of the tunnel diode. It is very, very important because it is operating in the negative resistance region. Negative resistance region is nothing but decreasing of the current as we increases the voltage. Generally, in normal condition, what is the point? If you increases the voltage in p-n junction diode, the current will increases. But here, some portion of the characteristics of the tunnel diode, that is A to B. So as we increases the voltage, applied voltage, the current is decreasing. Okay, so this is region is nothing but negative resistance region. Okay, generally here, if you increases the voltage, automatically current increasing proportionally here. But here it is what happened, current decreasing. So that's why it is called as negative resistance. Why it is resistance here is nothing but V and I. V is equal to IR, R is equal to V by I, right? So both are proportional there. But here what happened here, it is increasing as we increases the voltage. So the current is decreasing. That's why it is called as negative resistance region. Okay, so here at the starting point there is no current, tunnel current. After that, if you increases the voltage, what happened here? So there is a sharp increasing in the tunnel current up to this point A, and it reaches its peak value. So this voltage, the voltage at which the tunnel current reaches its maximum value, is called as peak voltage. So after that, what happened, from peak point to it goes on decreasing as we increases the voltage, and it reaches the valley point. Okay, so the minimum current that is flowing through the tunnel diode, at which the tunnel current is zero, is called, that is nothing but valley point. So it looks like valley, or it looks like valley. That's why it is called as valley region or negative resistance region, valley point. After that, what happened, if you further increases after that valley voltage, so what happened is here, so there is a current rise. It acts as a normal p-n junction diode operation. So this is what the characteristics and tunnel diode operation. Okay, so and we have many applications here for tunnel diode. Advantages of tunnel diodes are it has long life and high speed operation and low noise and no power consumption. So because why I mentioned here no power consumption means, low power consumption means, as we increases a small amount of current, automatically the current will rise maximum current, maximum value, that is peak point. Okay, so here, but here the negative resistance region of this tunnel diode has many applications for us. Okay, so we can have tunnel diode applications. Here application of tunnel diodes. Tunnel diodes are used as a logic memory storage devices. Okay, used as logic memory storage devices. Tunnel diodes are used in relaxation oscillator. So already we have seen about the negative resistance region. Whatever the diode or whatever the unijunction transistor, also one example for operating in a negative resistance region. So whatever the device, electronic device that operate in negative resistance region, means we can consider that one as we can use that one as a relaxation oscillator. Okay, so next we are going to discuss that UJT also. Tunnel diodes are used in logic memory storage devices. Tunnel diodes are used in relaxation oscillator. Next, another application is tunnel diode is used as ultra high speed switch, because for a small voltage there is high amount of current will flow. That means the tunnel diode will goes into the on condition within a given immediate time, that is within a less time. So that's why the speed of that circuit switches means what, if you on the switch, the current will flow. So that is a small voltage here if you apply. So the tunnel diode is on condition, goes into on condition, and the current will rises sharply. So that's why here switch, it can be, tunnel diode is used as a ultra high speed switch, and tunnel diodes are used in FM receivers.